does not seem to be leaking. All right, so the water level is here in the tube, and it's about roughly the same here. So the question is, where would we expect to see that first harmonic occur? Well, I've got a 320 hertz tuning fork here. So my frequency, 320 hertz. The speed of sound, it is temperature dependent, but we're not really going to worry about the temperature dependence right now. It's going to be roughly 340 meters per second. So, where would you expect the first harmonic? What would be the length of air? In other words, what's L? What's the wavelength? If I know the frequency and the speed, what is the wavelength? And while you're doing that, I feel like I should clean up the water that is in the hallway before someone slips. So what you got?
Speed over frequency,
Okay.
which is 1.0625 meters.
Yes. It is a length. All right, so if that is the wavelength of the sound being produced by this, how big does the air column need to be to produce that first harmonic? Okay. All right, so 26.6 centimeters. Now there is a, oh, of course there's still a leak there. So somewhere around here, there's measuring tape on the side here, and for some reason, I haven't quite figured out why. When we ordered these tubes a couple years ago, longer than I'm thinking, all of the tapes start at 2 centimeters below the top. So whatever we get, we're gonna add 2 centimeters to it. Now we can adjust the level of the water just by moving this up and down, and also has a lovely bonus that as this thing moves down, you get to hear metal scrape on metal. Let's see if I can do it more quietly than that. That seems to be working okay. Straighten that out some. Start below there. That is sad and pathetic. All right, let's do it differently. Frankly, that is the worst I've ever seen it done. In terms, or the worst. It's usually more blatant. A little below. There we go. Let's get it well above so I've got time. Hopefully you heard that volume go up. That's about at the 23 centimeter mark. Add the 2 centimeters, we get 25 centimeters.
That was a lower pitch, right? It was like a, not the high pitch ding. Cause that's all I was hearing before.
Oh, it was the high pitch?
Yeah.
It should be the same frequency either way. What would cause a difference in the sound? One, I tinged it, but I feel like doing that, it was more powerful in the fact that it was longer lasting, but that was definitely a sharper sound. All right, we can do that one more time, now that it's working. It's fading off there. A little bit past 23 centimeters that time. All right. So where would you predict the third harmonic?
.799 or meters.
All right. So that should be way down there. One of the issues with this lab is that when you start going down farther, water's gonna be coming up in this, and so it's usually convenient to get rid of water. .80 centimeters is around here. Instead of dumping it in the trash can. Let me get closer. And that was somewhere around there. It was about where we expected it to be. I assume you could hear it get louder. It's a lot of fun doing this, the lab associated with this in a room full of people, because frankly, everything sounds the same, sounds the same, pretty much the same to me. Very difficult for me. All right, so some credibility of what we're talking about here. And then the last one is, we have 2 free ends predicting those frequencies. so we have two open ends here, therefore two free ends. Questions on one fixed, one free before we do the two free ends? All right, so two free ends, which means I'm going to have nodes or antinodes.
Antinodes?
Okay. The simplest one I can do is this. So that distance there is L. How many wavelengths is that? The next simplest.
It's one wavelength. Three halves.
We'll add others at the moment, eventually. All right, so assuming that the speed of sound is somewhere around 340 meters per second, which is reasonable. As I turn this thing around, the air at this tip, at the far tip, well, I'll let you finish writing. The air at this tip is going to be moving faster than the air at this tip. The part that's sitting still, as this goes through the air, it is dragging air with it. Air is traveling faster up here than it is down here. Because air is traveling faster, the pressure at this end of the tube is less than the pressure at this end of the tube. Pressure at this end of the tube should just be the normal ambient pressure. And at this, it's been dropped. So because there's less pressure at this end, air will get sucked up through the tube. You can notice this also if this did not have the ridges in it, if it were just, like gray pipe, something that's flexible, you can spin that around. You don't get the whistling sound, but you definitely get a different sound of, there's a different frequency of the air as it goes through it. So as I spin it around, what frequency would the first harmonic be? Well, I know that frequency times the wavelength is equal to the speed. I know that the frequency is therefore the speed divided by the wavelength, which is 340 meters per second, divided by the wavelength. Well, I don't know what the wavelength is immediately, but I do know L. That's L, that length. I'm going to stretch it just a little bit because it does stretch a little bit as I swing it. And we end up with 84.2 centimeters. Or 0.842 meters. And therefore, the wavelength for the first harmonic.
Did you say 2.4 or 4.2?
4.2.
Okay.
I might have said opposite, but it is 4.2. Say it again?
403.8.
Ooh, wrong way. For the first harmonic,
I got 201.9.
Oh.
the wavelength should be twice L
Yeah.
for the first harmonic.
So 340 divided by 2 times 0.842.
Oh, you went to the next step.
Yeah.
What's the wavelength? That
Oh.
would be 1.684.
Yeah.
All right, so we end up with
201.900.
units?
Hertz.
All right. Is that 201?
Use my.
Let's see if that works. Let's see.
It's getting 364 hertz.
Okay. So one thing is, that's not the first harmonic. In order to get the first harmonic, I'm spinning it so slowly, there's not enough difference in air in order really to get the sound. So what we're hearing is actually the second harmonic. So let's do that. So for the second harmonic, I know that the wavelength is equal to L, so 0.842. And so the frequency for the second harmonic is 340 divided by 0.842.
Was 403.8.
And what you were getting was 364?
I'm not sure now.
Shall we do it again?
About 370, somewhere between 369 and 375. It doesn't have great precision.
$372. So we're off by about 10%, very crudely. Now, if I swing it around this way, it should sound a little bit different to you than it does to me. So again, that's swinging it like this, and now swinging it the other way. Does that sound different to you?
Too much.
Sounds the same to me.
Same? Okay. I was thinking there was a Doppler effect thing going. Some students have talked about that in the past, maybe more noticeable at the higher frequencies. Because it'll be spinning faster. All right, so let's make our prediction for the next one. What is the wavelength for the third harmonic?
.421 meters.
0.421.
Oh wait,
Yeah,
I did 1/2.
the 1/2 only works the first time. It's 2/3 that, should be 2/3 times that.
This is, wait, 3/2 or 2? Oh, is this inverse?
The wavelength is 2/3 times L.
So 0.562 or 1.561.
Like 561 meters, and so the frequency, 340 divided by 0.561.
605.7.
62? Off by 40, so percentage wise, I think we're doing better. Because that's now